So welcome everyone to the performance and capacity stream. My name is Piara and I'm going to be chairing this session. We're very pleased to have John from IntelliMagic, who will be presenting on the types of information available from your SMF type 42 records and kind of how we can use that when we experience any IO related issues. We'll have some time towards the end to ask John any questions, so do feel free to use the chat box as we go along. As with all of our sessions, we'd appreciate if you could leave us some feedback at the end, and I'm going to put a link in the chat box with the feedback page, and it only takes less than 60 seconds to complete, so we'd highly appreciate that. I'm now going to hand it over to you, John, to start the presentation.
Thank you very much. Good afternoon. As you can see, John Tissick is my name from IntelliMagic. I'd like to talk about IO and specifically what we can get out of SMF42 IO statistics. So I'd like to look initially at the general view that I think we all know and then dig a little bit deeper. Now, I will turn my camera off. I just wanted to make sure you could see who I am. I am living in the countryside and my bandwidth here is not exactly great. Okay, so let's move on. What I'd like to look at initially is how we typically look at disk performance, as far as I've gauged. And I'll give you some information as to what we've been looking at typically for disk performance. And then I'd like to branch into the SMF42 data, the IO statistics specifically, to see what additional kind of data we can get and why those kinds of records are actually very interesting for us. So just one slide on our company. IntelliMagic is based in the Netherlands. Some of you probably know us. We like looking at performance data and capacity information. We work closely together with other companies as well, and we enjoy what we're doing. And we have offices in the Netherlands, in Germany, and also in the United States in Dallas. So let's look at what I've termed disk performance. And I'm looking at data coming from or collected by RMF or by CMF. So I'd like to look at initially what I've termed the IO service time components, the traditional things we've been looking at that hopefully we all know about. And then I'd like to look at what RMF and CMF provide in, I've labeled it new metrics. New is not really that new. It's been around for quite a while, but there are some customers who still don't gather this information. And I'd like to just show you that it is interesting information that we should be looking at. Okay. So let's look at this first part, namely traditional IO. I'm including an RMF post-processor report based on the SMF74 subtype 1 data. And let me just have a look. Yeah. So what we're looking at here is a disk system which is not very active. Okay. And I've highlighted just one particular volume, purely just to look at some of the components of response time that are available in this static report. Now, one important thing to remember is the IO count that we're looking at here, which is in the device activity rate, refers to start subchannels. And we'll see why that's important to distinguish between what we're looking at here in the IO count and in some of the other reports. You can see highlighted in red the response time and then some of the components of response time, like iOS queuing, pending, disconnect, etc. I'll explain those in a little bit more detail in a second. You'll see something called interrupt delay time, int DLY. And in the volume I've highlighted, it's 0.128 milliseconds. The reason I've highlighted that particular volume, even though it has an extremely low IO rate, is just to highlight that the response time in this report does not include the interrupt delay time. And you can see that it's a combination of the pending and the connect time. Okay, that's just important. So if we look at this visually, and we're using our IntelliMagic Vision software here to look at the data, the I/O service time for a particular day, that's what I'm looking at, is made up of these components. Now you notice that in our representation, we actually do include interrupt delay time, which is light blue here. Because as far as the application is concerned, the I/O did take so many milliseconds, for example, and part of that was actually the delay for processing the interrupt. So these components from response time, like iOS queuing, then we're just waiting to actually get the I/O out and running there, and pending, disconnect, etc. For us, is important and very interesting to look at the health of the disk system as a complete entity. That's how I'd like to phrase that. So I think this is something that we probably already look at to see, is our disk responding well? Where are the peaks? And then maybe why are the peaks there? So just one additional point on interrupt delay time. It's extremely small in this particular sample here. I have seen very large interrupt delay times, which does mean that your response time will be higher. And the question is, what can you do about it? Interrupt delay time, firstly, there are options in PalmLib that need to be set for the correct ZOS, or rather Z series architecture. IBM has recommendations for that. Please verify that for your level. And also, if you see interrupt delay times which are high, maybe look at the dispatching of that particular LPAR and the weights, that it's not getting what it needs at that particular time frame in order to service those IOs. Okay, so that's service time. Another chart, or rather table, data that's interesting from RMF, CMF, I call the cache report. Data is in SMF 74 subtype 5. So the first thing I want to say is the IO count here that you're looking at, the IO rate in this table, is not start subchannel, it's a locate record. It's different. Okay, one start subchannel may have multiple locate records in it. So be careful if you're comparing those two. So this kind of data gives us very interesting information, also on the volume, or rather on the device basis, for the cache activity. Cache hits, misses, reads, writes, etc. So really good data to look at. Again, looking at it visually, I'm only looking at the locate record rate here. We can see how busy this actual disk system is based on the cache statistics. And again, here I've noted on the slide, one IO operation starts subchannel may contain many locate requests. Okay. Okay, so that's what I would call the classic metrics that we all know and love. New metrics, as I said, not really that new, is something like the link statistics. Another report, sample, post-processor report, you can get this by specifying ESS. The data is stored in RMF 74 subtype 8. So the link statistics gives us information about the ports, i.e. the interfaces, for FICON, for fiber, for PPRC, reads, writes, operations, things like that. Let me move on. Looking at it visually, what we can get out of this kind of data is configuration information. We can see the ports with a reasonable understanding of the naming convention for the ports and for the links. We can put together actually a host adapter view, a card view. We can look at utilization at that level. Okay, so the configuration information is very important. And of course, the operations throughput and response times for read and for write. And of course, FICON is what we're really interested in, and PPRC when we're mirroring data. Some customers actually have shared workloads, which means some non-ZOS systems using a disk that they've installed, and you'll see that as SCSI activity. What we can also get from the SMF74 subtype 8 are rank and array statistics. Now, you may not get this for all of your disk vendors, but definitely for IBM and for HDS, okay? What we can see here are extent pool informations, rank information. So very, very interesting, detailed, we use the term back-end activity. So let's have a look at that visually. One example here is looking at the response time for the two RAID groups that we have. It's a very, very small box. So in your environment, you'll see much more activity than this. Again, here we can get very interesting configuration information about the extent pools, about the rank groups, the RAID scheme, and of course, read and write operations, throughput and response time. So very useful statistics to have. So just putting together the configuration information, you'll see that we have RAID group information, front-end adapters, okay, the host adapters, or rather the front-end adapters on the disk, and of course things like the SSID configuration in the disk itself, what you've defined. So even though we're looking at performance data, normally we get a lot of good configuration information from these records as well. So don't ignore that. Okay, so what can we see with our classic RMF, CMF data? We see an overall view of the disk system. Sometimes we have to aggregate the data. By that, I mean some of the data is collected at an LPAR level. Some is collected at a disk hardware level. Okay, so you have to be aware whether you need to add the data together from the LPARs or it's sufficient just to get it out of the box, so to speak. So we see things like front-end service times, cache, link, configuration, information, RAID stuff at the disk system level. And we can look at a particular volume or an LCU or SSID, and again, look at activity and response time. So one important thing to remember is we have intervals for our RMF or CMF gathering timeframe. So that means that when you see a response time for a volume, that's the average response time for that interval, which may be 5 minutes, maybe 15 minutes. Okay, so be aware of that. Looking at averages rather than peak information in this kind of data. Great, but what do we sometimes need to see? Detailed information about what data sets are active and what is their response time. Now, we want to also see, well, are we talking about traditional Ficon IOs or are we talking about Z hyperlink synchronous IOs? That's becoming a little bit more prevalent in our environments. Maybe the volume activity and response time, we want to look at breakdown of the IO interrupt delay, or things like reserves or long busy, which are definitely affecting our IO response times. Then we have a topic which we've termed uncaptured IO activity, things, IOs that we really can't trace back to a specific address space or activity, monitors, things like that. Okay, so it's a more detailed view of digging deeper into what we want to see, not at a higher disk level. So let's get to the SMF42 data finally. Namely, SMF42 data produced by or written by TFSMS, many, many different subtypes and auditing. And unfortunately, there's no easy way to look at this data. I've included Palm members, IGDSMS and SMF Palm. As far as synchronization of the data, you can certainly do that, and it's interesting to synchronize it with RMF and your global SMF interval. And also in the SMF Palm member, make sure you're actually recording the 42 records. You may have turned them off for some reason. So that's just a general piece of information. SMF42 has many different subtypes. Here are some of the subtypes that are interesting for us for the IO activity. Okay, subtype 1, looking at the storage class activity, control unit subtype 2, or 5 and 6, where we're looking at VTOX or dataset statistics or dataset information. And of course, synchronous IO. So a lot of very interesting information with the 42 records. But I'd like to just give you a little bit of a warning. It can be an extremely large amount of data because we're talking potentially about a lot of dataset statistic information that's being produced. So be careful. That means small steps. I would personally start with one of your LPARs and turn on recording. Slowly look at how much is being recorded in volume, and then slowly work your way through your other LPARs, okay? And you can just do that by looking at your SMF PAR member for that specific LPAR. That's how you do it. Some possible ways to reduce how much data you're producing, or mainly the impact of the data volume. I hope we're all using log streams and not the sys1man data sets. That's a good way of reducing the pain, maybe, of having a lot of these records, potentially a dedicated log stream. I find compression for SMF recording is very good for reducing the amount of data stored on disk. And also maybe your processing of SMF data, if you keep daily or weekly buckets of data before they go to tape, they should also be compressed, okay? So there are a few things you can look at in order to reduce the pain, if it is painful for you, to look at and generate the 42 data. So let me just look at some sample charts of what we can look at in this data. What I'm looking at here is the top 15 datasets by IO rate. So we can see the cache-related information, i.e. read hit or read miss at a dataset level, okay? Whether random writes, whether sequential rate of the IOs is. Okay, so this kind of data is interesting to see at a dataset level, what kind of effectiveness we have as far as our cache, disk cache is concerned. And as you can see in the bottom right, I've written down where this data is available. So this is in the 42 subtype 6. Sticking with cache effectiveness, but now at an address space level, okay? Typically, when we think of address spaces, we think of the SMF30 records, but in the 42 records, we have a lot of good information where we can tie it back to address spaces, okay? So here again, we see at an address space basis or level, how effective the cache is being used. Are there cache misses? What's the read? What's the sequential and the random write rate? Okay, so a lot of good data in the 42 subtype 6. Some customers ensure that their data is encrypted, which is for some customers extremely critical. So at a dataset level here in the 42 data, you can verify if encryption is eligible for that data set, for that data type, and of course, if it is encrypted. Okay, so another very good auditing function, as far as I'm concerned, as far as encryption and data sets found in the 42 subtype 6 data. A couple of more sample charts before I get to actual some examples of what I would use this for. What we're looking at here is, again, at an IO basis, IO rate, for the top 10 data sets, and I've masked them with my names here. And what we're looking at is the captured FICON and the synchronous IO rate. And where you see the word synchronous, it means IOs running on Z hyperlink rather than on classical FICON channels, okay? So what we're looking at is the IO rate on a dataset basis, source from SMF42, subtype 5 and 6. Now, I use the term captured IO because we can associate it to a specific dataset and a specific address space. But in the records, you can actually find uncaptured IO information as well, okay? Monitors may be generating IOs that aren't easily tied back to datasets or maybe even address spaces, okay? Of course, response time is something that we really want to see as well. So we're looking at the response time here for the top 10 data sets, sourced again from the 42 data. So when you're looking at issues of high response time peaks at a disk level, you can go down to the SMF42 level and look at who is affected. Okay, and that's an important thing that I think we need to be able to do. I use the term uncaptured FICON IO rate. Okay, these are potentially monitors generating IOs, and we see these are specific volumes and the IO rate to that volume. Okay, interesting information just to see who is actually generating the IOs. Okay, that was just a brief introduction to what kind of charts we can look at based on the kind of data that we have in the 42s. So I've come up with some examples of how we can actually use this in our environment. So the first example is we have a large number of IOs. We'd really just like to know, okay, who's creating these IOs? Example number 2 is, okay, high response time. Well, who is affected and possibly who's causing it? That's a typical question that we get or that a customer has. Hey, we need to dig deeper into a problem to find out what's happening. And the third example I've labeled bonus example. Some customers are implementing Z hyperlinks and I would like to verify their usage. And that's the kind of data that we can have in numerous sources, but SMF42 is one of them. So let's look at the first example. Who is generating the IO? I've put together a table here with some of the volumes. I've labeled this the top 9 volumes, and I've sorted them by what I call IO intensity. That means the IO rate times the response time. So that means the busiest volumes are at the top. That's how we should interpret that. So we can see the most active volumes, response times. We can look at a specific volume, okay? And this is all based on the SMF42 data, and look at more details about that specific volume. So in the 42 data, we can look at who and which address spaces are generating the IOs and their respective response times as well. Okay, so to get a feeling for who is creating IO, this is a nice way of doing it at the address space level. So in this case, KICS or CICS is generating the majority of the IO. That was a simple example. Let's go to something a little bit more complicated and probably a little bit more useful as far as response time analysis. Who is affected by the response time peak? So based on our general data that we get from RMF or CMF, the 74 subtype 1, we can see the response time for a specific disk system. And we see various peaks, maybe during the batch time, maybe during the online time. So in this example, we'd like to look at the peak just after 5 p.m. and do a bit of analysis as to who's potentially suffering and then maybe who's causing it. So here again, I've put together a table with the top 10 volumes in this case around that 5 p.m. peak that I'm looking at. And we can see the response time for the volumes, the IO rate, and the components of response time. Is IOSQ a majority of the response time or connect time or disconnect time, etc.? Okay, so we get a better feeling for which volumes are affected and also what type of IOs, or rather the response time contributors to response time. Yeah. So this kind of information is from various SMF records. For example, the 74 subtype 8 that we looked at earlier. Okay, so it's different kinds of RMF data placed together. So let's look at one volume in more detail, the top DB2 volume. So when we're looking at a specific time at a specific peak, we can see, for example, the IO rate We refer to that as a front-end I/O rate. That means coming from the applications from MVS or ZOS. And it's actually relatively low, the red line here in this visual. We see the response time, orange line, is very relatively high, 2.4 milliseconds. And we also see what's called the backend drive rate. So now we're looking at data from various sources, still RMF data, yeah, but we're looking at the front end, i.e. what's generated from the LPARS view, the application view, and the back end, what the disk system is seeing, i.e. backend drive rate. Now, be aware the backend drive rate depends also on the RAID scheme and things like that, okay? So you may need to do a little bit of magic there to get the numbers you want. But the data is available in the 74 subtype 5, the cache statistics record. Okay, so we're drilling down a little bit further into this particular time frame. Who is affected by this response time peak? We have a list of our data sets on DB2001. So what we can now see, based on the SMF42 data, is the FICON, the captured FICON and synchronous I/O rate, also the response times, and also things like the maximum response time. That's interesting too, because that we haven't been able to get from RMF. Remember, it was an average for the interval. So now we can see a bit more information about a specific data set at that time frame, what kind of response time it was getting. Okay, and things like throughput and various other things. A lot of good information at a data set level now, based on the 42 records. Now, not looking at the data sets on that volume, but looking at the address spaces generating the IOs that are related to that volume, we now see the address space names. We see things like response time, IO rate, similar to what we saw at a data set level, but now at an address space level for this particular volume. So again, very interesting information that we can get out of the 42 records as to who is suffering and potentially who is causing. That's sometimes a little bit difficult, okay? So very good data. So I've chosen the top address space so I can look at the most active data sets for this DB2 address space. And we have information again on the IO rate and the response time and information about what type of IO as well. Okay, for example, read hit percentage is quite useful at a data set level as well. So that's an interesting example. Let me get to my last example, which is Z hyperlink. Customers are slowly moving towards implementing Z hyperlink. So if you are moving in that direction, how can you see how effective it is? So it's recorded in various SMF records. I've just highlighted the three records that we use here, the RMF, CMF device activity, and also the PCIe card information, okay, 74 subtype 9. And of course, the 42 records, namely the subtype 5. So let's see a little bit about what kind of information we can see here. So looking at Z hyperlink usage at a dataset type category, we can see, for example, linear datasets on the left and the categories of information such as synchronous write, i.e. Z hyperlink write IO failures or successes or eligibility or read misses. So a lot of good information about a specific dataset type, okay? But we can get further than that. So this is based on the SMF42 subtype 5 and 6 records here. If we look at a tabular view of the dataset types we're looking at, because some dataset types are Z hyperlink compatible and you can implement it, and some can't, okay? So let's look at the types of datasets we have, and we can see, for example, linear datasets. We can see the number of read hits eligible for synchronous IO, i.e. Z hyperlink IO, and actually how many were not attempted. We can look at maybe write requests if that's supported for that dataset type. So we get a picture here based on the 42 records of our dataset types and if they are eligible and if they're actually using the hyperlinks. And that's where we see what I've highlighted in green, the successful read IOs, for example. And what's also very important with Z hyperlink is the reads that didn't work with Z hyperlink and were redriven through the FICON infrastructure. So very, very interesting information to qualify what you've implemented. Is it doing what you're expecting it to do, and how well is it doing it? So just a couple more charts on Z hyperlink. So here we're looking at the synchronous IO for a specific service class, DB2, and it's by the storage group. So what we can see is the IOs direct to that storage group, whether they will read success or failures, and other information about eligibility for the IOs, and if they were eligible, whether it was successful or not. A lot of good information from the 42 records. When we look at Z hyperlink itself, and we look at the dataset response time for reads, for example, synchronous reads, we can see that compared to the classical FICON read, it's exceptionally fast, 22 microseconds compared to milliseconds. Okay, so this kind of information we get from the 42 records to verify that, yes, the response time is good for that particular storage group, for example. And finally, when we look at how well is our FICON and synchronous IO infrastructure performing as far as read IOs are concerned, we can look at what we term the front-end response time, i.e. the reads and writes for FICON, which is in the SMF 74 record. Okay, that's an RMF record. And then the average response time for all of the IOs. And we can then see how well the synchronous IOs have helped with the total IO response time picture. Okay, so this is not 42 records, but I wanted to include it because it's a nice summary of what our Z hyperlink IOs are doing. While we're on Z hyperlink, this is an interesting topic, and we do have customers who have both implemented and are implementing it. So one suggestion I would have, if there is interest in the audience, I can certainly put together more detailed information as to implementation and monitoring and effectiveness, basically, of Z hyperlink and synchronous IO. So give us feedback on that, and we can get something, or I can get something for you for the next round. So that's the end of my presentation. I hope there are some questions, and I'd like to pass it back to you, and we can take it from there if there are questions. Okay, thank you.
Thank you very much, John, for the presentation. So far, we've got no questions in the chat box. But yeah, just as a reminder, please do use the chat box to ask any questions. Now's the time. Or alternatively, if you've got questions later on, then can they email you as well, John?
Absolutely. My email is in the presentation that I assume you can download from the GSE website.
The website, yep. I'm just going to give it a few minutes, just in case people are typing. Okay, don't think we've got any questions coming in, John. So I think we can close it off there. Thank you so much once again for everyone joining, and special thank you to John for presenting. Just as a reminder, please do feel free to leave us some feedback, that'd be really appreciated by the QR code on the screen or the link that I put in the chat box.
Okay, thank you very much as well. I enjoyed it. And if there are questions, please send them directly to me, or we can move forward. Thank you very much.
Perfect. Thank you, John.
I was going to ask a question. Sorry, I'm a bit slow. Yeah, John, do you have a view on how early in the life of an IPL the data for 42 subtype 6, well, actually any of it is collected from? I'm thinking about things like, let's say the RACF data sets and things like that.
Yeah. My feeling, and I can't confirm it, is that that's why some of the IOs for RACF, for example, are unattributed, if I can use that term. Okay, so unfortunately, at the very early part of the IO process, we don't have the 42 records, and we don't have the ability, because SMS is the one who's doing it for us, to get that information. I would have to actually check to see exactly when we can clearly state that the data is then usable as far as pointing fingers at the address spaces that are running.
Yeah, I noticed you had at least one slide where I think it was at the volume level. There was RACF in the name. Now, I'm going to try and avoid outing somebody who's actually on this call who knows a lot about this stuff. I'm wondering whether people nowadays universally dedicate volumes to RACF databases, and therefore the instrumentation is kind of useful. Because if RACF comes in too early, then you wouldn't get the dataset level stuff, which would be a bit of a shame, but that might be the way it is.
Yes, so you're waiting for a response from someone else, I hope.
No, I'm not actually.
Okay.
he might want to wade in on the conversation, but no, I was just thinking the volume level you might have it. But what I don't know is how useful it is to know a volume level where as in your example, you had RACF in the name of the volume.
Yeah,
that's all I was thinking about. And there will be other data sets, not to generalize a bit. There'll be other data sets that are probably equally early that we don't tend to think of.
Yeah,
probably we see no footprints in the sand whatsoever for them.
Exactly, yeah. I will look at the RACF data sets on our system just to verify that we actually see data set statistics with the data set name or not. Okay, I can get you that information,
Right,
and then you can maybe distribute it, yeah.
I'd genuinely be interested in that, actually.
Mm-hmm. Yep, it's been noted.
Thanks, mate.
Okay, we do have an answer in the chat, by the way, from Mark Nelson. Thank you, Mark. Oh, let me read it out. For a non-VSAM RACF dataset, RACF is its own access method, and it is opened in a way that makes the 42 subtype 6 records not generated. Okay, so we can verify that, but thank you for that information.
Yeah, I've just given Mark unmute privilege, so hopefully he can speak if he'd like.
Oh, thank you very much. Appreciate that. Yes, thank you for reading the statement. For a non-VSAM RACF data set, we basically are our own access method. If you're using VSAM as your RACF database, which you can do starting in ZOS V2R5 with a certain OA 6267.
Sorry, Mark, it sounds very faint, the voice. I think if you can move closer to the mic.
Let's see, is this any better?
No, it still sounds very, very faint.
Is this any better?
It's still the same, unfortunately. But I could just about make what you're saying. But yeah, I mean, you can carry on, and we'll try my best to understand.
Well, let's see, is this any better?
Oh, a lot better, yeah.
Good,
Perfect.
good. Too many microphones, too much technology. Yeah, what I was saying was that a non-VSAM RACF data set, which is what you've had since 1976, we're our own access method, and the data set is opened in a manner that precludes the generation of the SMF 42s. If you starting in ZOS V2R5, you can have a VSAM RACF data set. There's an APAR that you need to make it actually useful, OA 62267. That allows you to share a RACF data set, to encrypt a RACF data set, and a whole bunch of other things. The open process there is completely different. And I would be interested to see if the 42.6 records are created. I have reports that they are. My personal testing, I have not been able to create them. But for performance testing, people did, and that's the important thing. And that there may be a difference whether you've activated the RACF data set, inactivated, or very inactive, or very acted it, because that will cause something to occur much later in the IPL process.
Okay. Yeah, thank you, Mark.
You're welcome.
Yeah, thank you, Mark. So yeah, so no more questions coming in the chat, so I think we can close it off there.
Okay.
Thank you
Thank
very
you.
much. Thank you all for tuning in.